Oh, uh, greetings, Professor. My name is Cheng Hao Min, who was a student of the courses Dynamic System from Xiamen University, Malaysia, student ID MAT 2004144. And today I will be presenting a study focused on the mathematical aspects of dynamic systems, particularly discussing the uniform oscillator and the beat phenomenon. So let's look at the structure of this presentation. We will initially focus on the basics of vector fields on a line and then shift our attention towards vector fields on a circle, which we will be mainly discuss about it in this presentation, followed by an introduction to a simple oscillator model known as the uniform oscillator. And in the end, we will discuss a fascinating and interesting concept known as the bit phenomenon. So in previous study, we have been solving most of the dynamic system equation looks like x dot equals to fx, which is just it tends to visualize as a vector field on the line. But today we will introduce a new differential equation that corresponds to the vector field on a circle with radius 1 and explores a simple model known as uniform oscillator. So, and discuss the effect known as beat phenomenon. So let's start our first major part. By here we will talking about the concept called vector fields on a circle. By labeling each point on the circle defined by a unit circle which radius is 1, which a circle with radius 1. So according to its angle corresponding to the origin, we could define a equation theta dot equals to f theta equals to f theta, which theta varies with the time t. So theta is assembling as the point of a circle corresponding to origin varies with time t, as we mentioned, and the rate of change of theta based on time is just known as the velocity vector of that point. And f theta is defined as a smooth enough two periodic real value function, so we can ensure that the theta dot is uniquely defined and exists everywhere. So as we mentioned, it was defining vector field on R1, which is the circle with unit radius, by assigning each point on the circles a unique velocity vector. So although the circle is one-dimensional, same with the vector field in line we discussed about earlier, but it has a different characteristic. By flowing in one direction, the trajectories will eventually return to their initial place by exactly two shift. Well, here I mean was just one revolution, which is 2 pi. So in the first time for our classes when studying the dynamic system, periodic solution has become possible for the first time in our classes. So let's look at the classic example written in the book, Nonlinear Dynamic and Chaos, which is theta dot equals to sine theta. So as we can see when we visualize the graph as the graph you see here, the vector flow was flowing counterclockwise for the upper circle and clockwise for the lower circle. But both of them are flowing from the unstable fixed point theta naught equals to 0 to the stable fixed point theta naught equals to pi. And to ensure periodic solution, we will treat 0 plus prime 0 plus prime 0 plus 2 pi as the same to ensure the velocity is unique defined. So in conclusion, vector field on a circle is a rule that assign a unique velocity vectors to each point of the circle. So we now introduce a basic dynamic system model known as the uniform oscillator. This model follows the simple differential equation theta naught equals to omega, which omega is the angular frequency here, uh, which determine how fast the point moving based on time. So solving this ODE give us the solution theta equals to omega t plus theta zero, the initial position of the point. So let us let us look forward to the other classic example written in the book. So two joggers, Speedy and Pokey, are running at steady pace around a circular track. Their pace are not slower down and boost up based on other people's acts. So they are considered as independent runners. And it takes Speedy T1 seconds to run once around the track, whereas it takes Pokey T2 seconds, which T2 is larger than T1 seconds to run around a circular track. So of course, Speedy will periodically overtake Pocky as he was faster. So the question is, how long does it take for Speedy to lap Pocky once, which leading him one revolution, assuming that they start at the same place together at the same time. So we could treat for solving this question, we just want to show that how long the time does it take for the phase difference between Speedy and Pokey to be large enough to equal to 2 pi, which is the angle of one revolution. So we had observed that define the phase of Speedy by theta 1 with here is Pokey with phase of Pokey by theta 2. We observed that for theta 1 equals to omega 1 equals to 2 pi over T1 times T, and the same for the theta 2. Suppose the runner begins to run at theta 0, the initial condition, then after calculation, we could derive this formula that for overlap one revolution, the time requires 1 over the inverse of 1 over T1 minus 1 over T2. So here we find an interesting behavior. Although that both runner action was considered as non-interactive, independent, and indeed with no correlation, we still discover periodic interactive between them. So this special effect is not effect, but phenomenon was called the beat phenomenon, so that two independent oscillators with disparate frequency will undergo periodic phase synchronization and desynchronization. So, uh, so we just the classic example again for the textbook question. So classic two bells problem. Different for different pace of the bells, how long does it take? Will they run and will they rank together harmonically the next time? We want to calculate the period of them to overlap. Let's say superposition. That time was superposition between each other. So using the formula we derived just now, and as we know that and the one bell rings every 3 seconds, which means the period of T1 equals to 3 and periods of T2 equals to 4. So using the formula, we will have the conclusion that every 12 seconds the two bells will ring together and create some sort of a superposition effect. So it will become louder, and we will only hear one sound like one bell ringing instead of two. So after we discussing for the long time for the whole presentation, I will want to please allow me to do a little experiment to have a better understanding for the beat phenomenon using a multiple tone generator. So I'm sorry, but the volume will may let other feel uncomfortable, a little bit uncomfortable. So I advise you to lower down your volume. So okay. So I will use this multiple tone generator to generate two sine wave frequency with different frequency. So as we know that the frequency is just the inverse of the period. So for this case, the two frequency have difference for one. So for one, the inverse period t equals to one. So we will hear interacting, or we will feel interacting when we play both frequency for every 1 second. So I'll lower the volume a bit to let it, to let it. So let's get started. Yes, as you can see that the volume will disappear for every 1 second in a 1 second period. And if we increase if we decrease the difference between them, so in this case, the frequency difference is just 0.25. With the inverse, it just the period was equal to 4 seconds. We will hear a much slower overlapping behavior when we hear in this case. So as you can see that this time it takes 4 seconds around to let us observe the overlap superposition behavior, so the sound was disappear. So vice versa, when we increase the difference between them, the frequency difference between them. So in this case, the frequency difference is 10. With the inverse, it was 0.1. So you will hear a rapid burst for every 0.1 seconds. So here are some very interesting behavior on for this beat phenomenon. So yeah, using a special property, musician will always apply this effect on tuning the instrument using a pitchfork or something, two pitchfork. When you knock it with each other, it will generate a interesting sound. So although the presentation is not that not that desire, not that completed, but I hope we will have a better understanding, or at least has a little interest in studying on this wonderful effect. Thank you, Professor, for listening to this not that good presentation. Thank you.